Hey guys, welcome to STAT 441 at Virginia Commonwealth University. In this lecture, we will learn about how to create confidence intervals for population proportion. So far we have seen how to create a confidence interval using the central limit theorem for mean and then comparing two population means. Uh, the next parameter of interest is population proportion. Again, it is a useful parameter where we are trying to figure out the proportion of successes in a given population. So you can think of this as a binomial proportion P of successes. So think of the binomial experiment. Here, we are interested in the proportion of elements in the population that have a certain characteristic. A couple of examples here. A quality control inspector may be interested in the proportion of defective items produced on an assembly line. On the other hand, a supplier of heating oil may be interested in proportion of homes in its service area that are heated by natural gas. In both cases, the population is pretty large, and to get the actual value of the proportion might not be practically possible. So we would like to estimate this value using confidence intervals. So here is where we start. We will start by finding a point estimate. So basically, we will pick a sample from the population and we calculate the sample proportion, which would be the most logical point estimate. So if y is the number of successes in the sample of size n, then p hat, this p and a little hat on top, p hat is the sample proportion, and it is equal to y divided by n, where y is number of successes of a binomial experiment. Okay, so we can again apply the central limit theorem here for the binomial distribution, because the binomial distribution is nearly normal as n becomes large. For values of the distribution of y will be symmetric with the mean n times p. Remember, binomial distribution has a mean of n times p. So when p is not close to 0 or 1, the binomial distribution will be fairly symmetric. Close to 0 or 1, it will be skewed, and therefore we cannot use the central limit theorem. So for values of p which are not close to 0 or 1, and if we have a large n, then we can use this method. So how can we figure out what the distribution will be like? So for large n, p hat will be approximately normal. The mean will be expected value of p hat, which is p, which is the proportion of the population, and variance will be p times q divided by n. Again, this information is coming from the binomial distribution. For a large sample, the confidence interval can be created like this. If you remember, for theta hat, we had this setup which we used earlier. So again, p hat plus and minus the alpha by 2 square root of p hat q hat divided by n, where alpha by 2 is basically if we have a 1 minus alpha times 100% confidence interval, then alpha by 2 can be calculated using this. So 1 minus alpha, let's say, is a 95% interval. So 1 minus alpha is 0.95, alpha is 0.05, and alpha by 2 is 0.025. So we can find this value from the table. The assumption here is that the sample size is sufficiently large. So the way we can test this is by finding n times p hat and n times q hat. And if both numbers are greater than equal to 4, then we have a large enough sample. So p hat here again is sample proportion, and 1 minus p hat is q hat. N is the sample size. Here's an example using this information. Stainless steels are frequently used in chemical plants to handle corrosive fluids. However, these fluids are especially susceptible to stress corrosion cracking in certain environments. In a sample of 295 steel alloy failures that occurred in oil refineries and petrochemical plants in Japan, 118 were caused by stress corrosion cracking and corrosion fatigue. Construct a 95% confidence interval for the true proportion of alloy failures caused by stress corrosion cracking. Okay, so here we have a sample from this population. We have a sample of 295, and after 295, 100 samples were caused by corrosion, or the failure was caused by corrosion. So our p hat sample proportion is 118 divided by 295, or 0.4. N times p hat is 118. So 295 times 0.4 is 118. And 295 times 0.6 is 177. Both numbers are more than 4. So we have a large enough sample. Okay. Now we need a 95% interval. So let's see what the z alpha by 2 value is. So for a 95% interval, 1 minus alpha is 0.95, alpha is 0.05, and alpha by 2 is 0.025. So basically, we need z alpha by 2 or z 0.025. So we will start here. We will start by finding t of 0.025, which is here, and the corresponding value at infinity degrees of freedom, which is 1.96. Okay, so z alpha by 2 is 1.96. This is an easier way to find the z alpha by 2 using the t table. Okay, and then it's just plugging in the information in the formula. P hat is 0.4, 1.96 is your z 0.025, square root of 0.4 times 0.6 divided by 295. When you add and subtract this quantity to 0.4, we get 0.344 and 0.456. So we are 95% confident that the interval 0.344 and 0.456 encloses the true proportion of alloy failures caused due to corrosion. Okay, now we can use the same method of confidence intervals to compare two population proportions. So let's look at a couple of examples to see where this can work. So here is an example. We may be interested in comparing the proportion P1 of defective items produced by machine 1 to the proportion P2 of defective items produced by machine 2. So P1 minus P2 is what we are interested in. To create that interval for P1 minus P2, we will pick two samples, one from each population. First sample size N1, okay. Second sample from the second population size N2. Count the number of successes in each one. So Y1 is number of successes in the first sample. Y2 is the number of successes in the second sample. And again, these are independent samples. So this gives us the two sample proportions. P1 hat is Y1 divided by N1 and P2 hat is Y2 divided by N2. And here is our confidence interval. P1 hat plus and minus z alpha by 2 and then sigma of P1 hat minus P2 hat. Again, using the central limit theorem, we can get P1 hat minus P2 hat plus and minus z alpha by 2 square root of, and this will be the standard deviation. Okay, again, you can see it's like a weighted average. So with this, we can create a confidence interval if we have a large enough sample. And to check that, we basically have to check this for both samples. So N1 P1 hat, N1 Q1 hat, N2 P2 hat, and N2 Q2 hat should all be greater than equal to 4. It's important that you check the assumptions and write it down, because if the assumptions are failed, we should not be using the confidence interval formulas. Okay, here's an example. A traffic engineer conducted a study of vehicular speeds on a segment of street that had posted the speed limit change several times. When the posted speed limit on the street was 30 miles per hour, the engineer monitored the speeds of 100 randomly selected vehicles traversing the street and observed 49 violations of the speed limit. After the speed limit was raised to 35 miles per hour, the engineer again monitored the speeds of 100 randomly selected vehicles and observed 19 vehicles in violation of the speed limit. So basically, let's look at the question once more. So we have two scenarios here. First, when the speed limit is 30 miles per hour, and the second scenario when the speed limit is 35 miles per hour. We're trying to compare the proportion of violations in each of these two populations or scenarios. We want to find a 99% interval for P1 minus P2, where P1 is the true proportion of vehicles that exceed this speed limit when it's 30 miles per hour. P2 is the proportion of vehicles exceeding the speed limit when it is 35 miles per hour. And then we need to interpret the interval. Okay, so we start by finding P1 hat and P2 hat, the two sample proportions. P1 hat is 49 out of 100, P2 hat is 19 out of 100. And then we check the assumptions, all four N1 P1 hat, N2 P2 hat, N1 Q1 hat, and 2 Q2 hat. They're all more than 4, so we have a large sample. Now, this is a 99% interval. So again, let's think about how to get the Z alpha by 2. 1 minus alpha is 0.99. Alpha is 0.01. Alpha by 2 is 0.005. Okay. So if we can locate T of 0.005 here, this is T of 0.005 corresponding infinity degrees of freedom. This will be our Z alpha by 2, and its value is 2.58. Now we need the interval by plugging in. We can create it by plugging in the values. P1 hat is 0.49, P2 has is 0.19, Z alpha by 2 is 2.58, and then this is the standard deviation. The interval values is 0.136 and 0.464. So our interval is that we are 99% confident that the difference in the true proportions is between 0.136 and 0.464. Okay, and the what can we know about the differences? So since the lower bound of the interval is positive, and of course the upper bound is positive as well, we can be confident that the proportion of vehicles when the speed limit is 30 miles per hour exceeds the corresponding proportion in violation when the speed limit is 35 miles per hour by at least 0.136, so approximately 13.5%. So that is confidence interval for proportions and comparing two proportions. Thanks for watching.